So moving on to part 2 of Article 430. So as we mentioned previously, parts are the divisions of an article which summarize or, if you will, clarify in a way it gives clarification for the rule. It allows you to understand. It organizes the specific requirement for that article. So this part 2 applies to the motor circuit conductors, the requirements for the motor circuit conductors. So it specifically states that in general that the part 2, it specifies the ampacity of the conductors that are capable of carrying the motor current without overheating under specified conditions. So what this basically means is that motor circuit conductors are required to have a minimum ampacity. That ampacity will depend on several situations. However, in general, the motor, in any case actually, in general, the motor will have to, the conductors which are carrying the ampacity for the motors have to be of a sufficient capacity to actually carry that the motor current. Now there are additional rules that apply to this. As far as the motors that are above 1,000 volts, Part 11 is actually used. So we do not use Part 2 for the requirements of the ampacity for those types of motors. Now, moving on, we previously mentioned, if we can recall, when I was speaking about the scope of this article, I mentioned that in any motor installation, the circuit conductors must be of sufficient capacity for the motor current. So this is actually a simple statement. However, it's general, but in precisely determining the minimum ampacity of the motor circuit conductors depends, as there are actually several cases, all of which apply to a single motor. So 430.22 applies to a single motor, and there are several cases that specifically address certain types of motors or certain kinds of or motors in certain configurations or things of that nature. We will just stick with motors of certain types of motors. So that is, in general, the conductors which supply a single motor. So conductors that supply a single continuous duty motor. So that is a motor which is which is used in continuous duty. The term continuous duty is actually defined in Article 100. So there's actually there's a definition given for it. So what it means for the motor to be in continuous duty. The word continuous duty, or the compound continuous duty and continuous load, they have similarities, but there's actually a difference. When you say continuous load, usually you're just basically saying by code definition, it basically means that a load that that is expected to continue at full capacity or whatever, at the full capacity for 3 hours or more. However, with motors, clearly the person cannot confuse these two, because continuous duty and continuous load is two separate things. But I'm just mentioning this just for for clarification. However, the continuous duty, when we say continuous duty in reference to motors, it basically means that it's a motor that is going to operate. Its time that it operates is not definite. So it will operate for an indefinite amount of time. So basically, not every motor is actually rated for continuous duty, but there are continuous duty motors they are rated. Obviously, the motor which is used in continuous duty obviously would need to be rated for continuous duty, but not every single motor is rated as a continuous duty. Really, when you say continuous duty, basically is in reference to what it's going to be used for. So whatever the apparatus or whatever the machinery or piece of equipment or whatever it may be doing, whatever it may be used for, if that thing will is in such a way that it will operate for a indefinite amount of time, then that motor is to be considered continuous duty. That means that that motor would actually have to be rated to be used for continuous duty operation. So, moving on, the motor, which is a single motor, the conductors which supply a single motor, and that motor is for use in, meaning that it's going to be used in continuous duty applications. In general, basically the capacity, the actual current carrying capacity, the conductors cannot be rated not less than 125% of the motor full load current. So this full load current is actually the current which is specified in the NEC, not the current which is located on the nameplate of the motor, or the amperage or the ampere rating that's located on that's marked on the nameplate of the motor. So this is general as stated here. And also, depending on the use, the situation, and the type of motor, basically, there are actually lesser values which are permitted to be used. That means that they are permitted, meaning that you cannot basically go less than them, but you could always go more, meaning that it's not exactly a requirement, but it is something which is an optional. It's permissible to do, but it's not required to do that. However, we are concerning ourselves with the minimum ampacity of these circuit conductors. So, regarding the case of a single motor, there are actually several cases that I basically mentioned. There are several cases actually. So if we have a single motor that's going to be used in continuous duty application, the ampacity of the conductors cannot be less than 125% of the motor full load current. So that is, supposing that we are in the case where there are conductors that are going to be used to supply a continuous duty motor that is used in a continuous duty application. That is, the ampacity of the conductors, they must be equal to or greater than 125% of the motor full load current. So in reality, what this actually means is that the capacity, the current carrying capacity of the basically, what this basically means is that the conductors have an ampacity that is increased by 25%. So that is that they are increased by 25% above the motor's full load current. So basically, I will actually explain this further. So it's pretty interesting because the 125%, it basically comes from the fact that, as it's stated here in the NEC, the 125%, pretty much here, it comes from the fact that it lessens the mathematical steps. So that is, there are two methods that a person can use to actually solve for this, and one results in less steps and the other results obviously in more steps. Okay, So I will basically explain these methods that pretty much yield the same result. So as I mentioned, one contains a single step and the other contains twice. So supposing that we are to determine the minimum ampacity for conductors that will supply a certain single phase 230 volt 1 horsepower continuous duty motor with a full load current of 8 amperes. So using the first method, we pretty much multiply 125% by 8 amperes, which basically equals 10 amperes. So in the second method, we multiply 0.25, which is basically 25%, by, that's 25% as a decimal, by 8 amperes, which equals 2 amperes. Then we have to add 2 to 8, which equals 10 amperes. So both methods are actually valid. However, the easier one is the first. That is multiplying 125% by the motor's full load current instead of taking 0.25 and then multiplying it that way than having to add. So as you see, both of these methods, they yield the same results. They're both valid. However, one's easier than the other pretty much. So at this point, it actually should be clear that the conductor's ampacity is larger than the motor's full load current by 25%. So this case is actually general, and it pertains to a simple alternating current and direct current motor. So we will further explain the additional requirements, the additional requirements and specified rules pertaining to certain types of motors. So as I mentioned, this rule applies to general single. It applies to a single motor that is using continuous duty, either as AC or as DC. This is the general rule for those. Now, in the case of the conductors, which will supply the direct current, so supposing that in this rule we have a direct current motor rectifier that they're supplied. So in the case of the conductors that supply a DC motor that is supplied by a rectifier, so I would like to actually elaborate just a bit to provide some context on the terminology of this section here, or of this this rule. So as we stated before, that direct current DC, so direct current, pretty much, we mentioned previously that direct current, that there are motors which operate off of alternating current, and there's motors that actually operate off of direct current. So in order to convert from alternating current to direct current, there are devices that rectify this pulsating or this changing current and voltage. It rectifies it so it can become more of a constant or direct current, if you will. So the rectifier refers to many things. It refers to many things. It's something which corrects. But rectifiers can refer to electronic circuit boards. It can refer to many different things. However, what I would like to speak about is something that is more close to our time and what we usually deal with in regards to rectifiers. Regarding this rule, that is the direct current motor rectifier supply. So in this case, the conductors that supply the DC motor, that is a single motor. I don't want to have to keep on mentioning we're talking about single motors. So all up to this point, we're still stuck on single motors. So in the case of conductors that supply single motors, it is a DC motor, that is, and it is supplied by a rectifier. So before we dive into this, I would actually like to discuss the terminology of the rectifier. So in past, before alternating current was introduced, direct current was prominent. So that is all electrical services and equipment, such as motors and so on, were DC. When alternating current became widespread, DC systems began to phase out of many facilities. So alternating current and direct current, alternating current, there was a time period actually that alternating current was sort of just thought as kind of like an experimental kind of thing. But at that time, which was over 100 years ago, direct current was actually the main source that was pretty much used. So the problem that happens is that in our present time, it is actually very, very difficult to it's very difficult to actually find direct current services because of the fact that single phase and three phase power alternating current is actually dominant. So there is actually still an issue. So what do we do when we come across, like, we have a DC motor and we want to operate it using direct current? So we have to use what is called a rectifier. That is a device which converts or rectifies alternating current to become direct current. So rectifiers, they are used in many applications, not just in motors. So whenever there is a need to convert alternating current to direct current, this is when they are used for the most part. So the terms here, half wave, single phase half wave, and full wave, single phase full wave type, this basically is it basically describes the method that is used to convert this AC to DC. So that is, in a half wave situation, the DC voltage is not as constant. So in a full wave situation, the DC is more constant and it is more close in comparison to the true DC voltage rather than the half wave. So eventually I'm going to illustrate this in the coming, but at this point the term rectifier should actually be understood. So with the background that we actually have, we will now talk about what the NEC requires, that the ampacity of the conductors that supply this motor, this rectifier, basically, that will supply eventually the motor. So as far as the ampacity is concerned, it is based on the input current that is marked on the rectifier, as we see here. So as far as the DC motors operating from a rectified single-phase power supply, so the conductors that are between the field wiring output terminals, that is, that the conductors that are between the output side, that would be the DC side of this rectifier, they are based on the motor full load current. So that is, for example, let's just say that we have a motor, for example. Let's just say, for example, that the motor has a nameplate value of 20 amperes. The rectifier has a nameplate value of 20 amperes. That is the rectifier, right? Because we base the ampacity on the rectifier, on the supply conductors first. So if the rectifier has a ampacity, a nameplate value of 20 amperes, then you basically take 125% and multiply it by 20. So that's 25 amperes. And this is the minimum ampacity for the supply conductors. As for the conductors between the rectifier and the motor, their ampacity is based on the motor full load current multiplied by the value of 190% or 150%. And that would be determined based on if the rectifier is of a half wave type or a full wave type. That is single phase half wave and single phase full wave. As we see, these values here do not apply to three phase types. So in this case, you pretty much it would be understood that clearly the thing to take from this is that the supply conductors that come in, that is the conductors that are on the line side of the rectifier, which is like the piece of the converter um, equipment. It is based on the nameplate, the input current of that rectifier, multiplied by 125% of the rated input current of that rectifier. And then the conductors that are on the supply side, that is the load conductors of that rectifier going to the motor, they are based on the motor's full load current multiplied by 190% or 150%. So from this point, we can clearly see that the rule of 430.22 was general. It was very general because in this situation, according to 430.22, okay, this rule that talked about the continuous duty motors and the single motor operating basically as continuous duty. So in general, it's based on 125% of the motor full load current. But there are additional rules that would apply to specific types of motors and specific types of equipments. Or so, for example, a motor that is being run by a motor rectifier, a direct current motor rectifier. So this is because we're not talking no longer about general motors. So moving on, in the case of the conductors that supply the multi-speed motor, so these multi-speed motors, they constitute a particular case. So it is actually of our interest to have some background to understand this rule. So these motors, when we talk about these multi-speed motors, these are actually motors that they consist of several windings. So the leads of these windings, they usually are marked with a high or a low speed. And in the introduction of this lesson, I actually did explain that motors consist of poles. So these poles, they are alternating in polarity. So supposing that a motor has two poles. So if a motor has two poles, that means that it has a north and a south. So if the motor has four poles, the same reason follows. So it has two norths and two souths. So supposing that if this motor that had four poles, so that means pretty much that a motor with four poles has a lower speed than a motor with two poles, given other factors are constant, which I will eventually elucidate on. In the case of an alternating current motor, the speed that the rotor will rotate at is actually affected by the supply frequency and the number of poles. That is, the speed is equal to 120, which is a constant, times the supply frequency divided by the number of poles. For example, if we were to energize two poles of a motor with a 60 cycle power supply, its speed will be 3,600 RPM. If the same motor had four poles and was energized with that same supply at that same frequency, with all the other values fixed, its speed will be 1,800 RPMs. So as you can see, a motor with lower number of poles will have a higher RPM at the same frequency with the same constant values as a motor with more number of poles. It will have a motor with more number of poles will have a faster, it will spin faster, it will have a higher RPM usually. Now this basically is actually the basis for, it is basically the basis for the multi-speed motors that's mentioned here in the NEC. So